In our very first video, we learned what is matter and how it started to exist. We also learned that everything wants to be stable or in a state of equilibrium. We briefly learned what natural forces govern the properties and behavior of matter. Such a study falls under the branch of chemistry called physical chemistry. The physical chemistry at atomic or molecular level is called molecular chemistry or quantum chemistry, whereas the study of matter at macroscopic level is called thermodynamics. In quantum chemistry, for instance, the interactions among electrons and between electrons and protons of one or more atoms are focused. In thermodynamics, on the other hand, the properties of the bulks of molecules related to equilibrium are under consideration. The cooling down of a hot cup of tea until its temperature comes in equilibrium with the temperature of its surroundings is a thermodynamics case. Today's lecture is the first one among the series of lectures on thermodynamics. Thermodynamics is the branch of science that has immensely changed our world. The Industrial Revolution, steam engine, and other related inventions are based on the exploitation of the principles of thermodynamics. First thing to be learned in thermodynamics is the distinction of a system and its surroundings. The part of the whole universe that is under consideration is called system. For example, a cup of hot tea, a can of Coke, thermos, sun, solar system, Milky Way can all be systems. And anything in the universe other than the system is called surroundings. Sun is an example of open system because heat is easily transferred to the surroundings. The can of Coke is a closed system because the gassy drink is enclosed at certain pressure. However, the can of Coke can be heated or cooled down, therefore it is a closed system, but not an insulated system. The systems that allow heat transfer are called diathermic systems. The systems that do not allow heat transfer are called adiabatic systems. Thermos is a system from which, ideally, heat does not transfer to and from the surroundings. Such a system is example of an adiabatic system. Thermodynamics is applicable in all kinds of bulk systems and surroundings. We start it with the simplest form of matter, the gases. Sometimes, gases and liquids are collectively called fluids because, unlike solids, both gases and liquids flow in free forms. The thermodynamics of gases can be described by their properties including temperature T, pressure P, volume V, and the amount of gas N. The properties that describe the state of a system are called state functions. 3 out of 4 state functions of a gas are enough to describe a gas, because fourth will be related to the other 3. Before we go any further, few things which are universally true should be kept in mind. The heat, pressure, voltage and flow naturally go from higher end to the lower end. The heat naturally transfers from high temperature region to a lower temperature region. The matter at higher pressure region will tend to go towards lower pressure region. Fluids naturally flow from higher regions to lower regions. Voltage or electric potential also naturally travels from higher voltage to a lower voltage region. However, voltage and flow won't be discussed today. Only pressure, temperature, volume and the amount of gases are the focused properties. The relation between all 4 properties of a gas can be found by performing a few simple experiments at ideal conditions. Ideal conditions are the assumed conditions at which gas molecules exist and behave in certain ways. The ideal conditions will be elaborated soon. The gas under ideal conditions is called an ideal gas or a perfect gas. In thermodynamics and all of physical sciences, it is very frequent practice to make assumptions. The assumptions make possible to derive principles and approximate model equations of a subject matter, which would be impossible otherwise. For example, in the first video of periodic table, all the atoms were assumed spherical, and atomic size was assumed to be the radii of 2 closely packed identical atoms. Many times, assumptions help achieve 99% accuracy without using highly advanced technological tools. Coming back to our original topic, that is, the ideal gas or a perfect gas. It is a gas in which all molecules are of a spherical shape and the molecules collide elastically. Meaning, when molecules collide, they respond like they are hinged to a spring. There are no attractive or repulsive forces between them. No gravitational force is acting on gas molecules, and molecules are widely spread from each other. The actual volume of gas molecules is negligible compared to the volume of the gas container. The kinetic energy of molecules is directly proportional to the temperature of a gas. Suppose a few samples are perfect gas on which some experiments would be performed to derive gas laws. Firstly, suppose there is a cylinder of a gas with a piston over it that controls the pressure. The cylinder has a fixed amount of perfect gas and temperature is also kept constant. As the pressure on the gas is increased, the volume is also decreased. Thus, there is a relation between pressure and volume, that is, the pressure of a gas is inversely proportional to the volume of a gas. P equals 1 over V. This was first reported by Boyle, hence called Boyle's law. Secondly, imagine another case in which the pressure and the amount of a gas is kept constant. As the temperature of gas is increased by heating the cylinder, the gas molecules will collide with each other more rapidly and will occupy more volume. Thus, there is a relation between temperature and the volume of a gas, that is, the volume of a gas is directly proportional to the temperature of a gas. This was first discovered by Charles, hence called Charles' law. Thirdly, imagine a cylinder of a gas at constant temperature and pressure. If the amount of the gas is increased, the volume occupied by the gas will also be increased. This was first reported by Avogadro, thus called Avogadro's law. Based on the supposed experiments above, we plot graphs A, B, and C. Graphs are very useful to study behavior of substances under certain conditions. Plots A, B, C are as follows. Each line in graph A represents a different gas, and all the data points are obtained at constant temperature for each gas individually. The curve in which all the data points are obtained at constant temperature is called an isotherm. Therefore, all these curves are called isotherms. It can be observed that, with the increase in pressure, volume kept decreasing or the inverse of volume kept increasing for all given gases. The curve in which all the data points are obtained at constant pressure is called an isobar. Thus, all the curves in graph B are isobars. Similarly, all the lines in C are plotted at different constant volumes, thus, curves obtained are called isochores. From the three experiments above, we also deduced three laws: P proportionality 1 over V, V proportionality T, V proportionality N. By combining all the three laws mentioned above, a general gas law can be obtained, which is as follows: PV proportionality NT, PV equals NR, T, R, is a constant of proportionality, which can have different values depending on the units of pressure, volume and temperature used. It is also called general gas constant. To calculate different values of R, we need to discuss state functions in some detail. The first state function to be discussed is pressure. According to International System of Units, SI, the unit of pressure is Pascal. 1 Pascal is equal to Newton per meter squared. Pressure is also expressed in atmospheric units called ADM. 1 Pascal equals 1.01325 into 10 to power 5 ADM. Another unit of pressure is bar. 1 bar equals 10 to power 5 pascals. Torr is also a unit of pressure, which is named after Torricelli, the inventor of earliest barometer. Barometers are devices used to measure pressure. 1 torr equals 133.32 pascals. Let's see how pressure is measured by Torricelli's barometer. Torricelli's barometer has a tube filled with mercury, which is 13 times heavier than water. Torricelli placed the inverted tube in a basin of mercury that caused some vacuum in the tube, and some mercury was left over in the tube. The change in the level of leftover mercury was due to the atmospheric pressure at the surface of mercury in the basin. That is why pressure has also the units of length. 1 torr equals 1 millimeter of Hg. This technique is still used to measure atmospheric pressure, which then is used to forecast weather. Let's also see on what factors does pressure depend on. Force is a product of the mass of the fluid and acceleration of the fluid, which in this case is gravity. Therefore, F equals mg and area equals A, then pressure P equals mga. We know that mass can be expressed as density ρ divided by volume. by replacing mass with density over volume, P equals rho over V into Ga. And volume is area into height. Then pressure will be equal to density over height of column into gravity. Notice that in the final equation, cross-sectional area of the column is not given. Therefore, pressure does not depend on the cross-sectional area of the column. This makes pressure an intensive property. Temperature is also a crucial state function. Like pressure, temperature also has more than one units. Temperature is measured by thermometers. The earliest thermometers were also composed of mercury columns or other fluids. Mercury, Hg, is liquid at room temperature and it expands when heated. This characteristic of mercury allows it to detect heat change. Because of that, mercury has been used in thermometers. The rise and descent of mercury in the column of thermometers determine the temperature. For the invention of Celsius scale thermometer, the level of mercury in a column was marked when thermometer detected heat change after being placed in the melting ice. The level on the column is also marked when thermometer is placed in the boiling water. The height difference between the two marks was divided into 100 degrees. That's why, on Celsius scale, the water boils at 100 degrees and water starts to freeze at 0 degree. This is also the reason that Celsius scale is not considered the absolute temperature scale. Different liquids expand differently. They will rise or descend differently when exposed to the same heat, and will show different temperatures for the same state of a system. The temperature measured on Celsius scale is denoted by theta, and its units are degrees Celsius. For an absolute scale, we recall Charles' law, in which volume of an ideal gas at constant pressure was directly proportional to temperature. Charles predicted that, if isobars are extrapolated to the lower temperatures, the volume of an ideal gas will eventually become zero. It turned out that all the isobars intersect Celsius scale at -273, which means that volumes of all gases become zero at -273 degrees Celsius. Keep this thing in mind, that this prediction is only based on the behavior of ideal gases. In reality, a gas will condense to liquid form before its volume becomes zero. However, the extrapolation helped to achieve absolute zero scale. It was revealed that the best way to measure temperature of a gas is to measure it in terms of pressure, which would be independent of the kind of gas molecules. Such a scale would be called a perfect gas scale. The boiling point of water should also not be defined in terms of degrees of temperature, but, in fact, it is the point when vapor pressure of water becomes equal to the pressure of the atmosphere. Water boils at 100 degrees Celsius at sea level, but at higher altitudes, at mountainous regions, water boils at less than 100 degrees Celsius. This is because the atmospheric pressure is lower at higher altitudes. From experiments, it has also been found that a perfect gas scale is actually a thermodynamic temperature scale. In this scale, temperature T is expressed in the units of Kelvin K. Thermodynamic and Celsius scales are related as T in kelvins equals theta in degrees Celsius plus 273.15. Fahrenheit is another scale of temperature which has units of degree Fahrenheit. Temperature units are interconvertible as shown here. Celsius into Fahrenheit. Degrees of Celsius is needed to be multiplied by 9/5, then 32 must be added to it. The resulting value will be the temperature in degree Fahrenheit. To convert Fahrenheit into Celsius, 32 must be subtracted from Fahrenheit, then multiplied by 5/9 as shown here. The interconversion of Celsius and Kelvin scale has already been shown above. Third state function we discuss is the amount of a substance, called mole. Mole is denoted by small n. It has units of mole. 6.02 into 10 to power 23 atoms, ions, molecules or other species of any substance is defined as 1 mole of a substance. In 1 mole of hydrogen, there will be 6.02 into 10 to power 23 atoms of hydrogen. In 1 mole of silver chloride solution, there will be 6.02 into 10 to power 23 ions of silver, as well as 6.02 into 10 to power 23 chloride ions. The number 6.02 into 10 to power 23 is named after Amedeo Avogadro, called Avogadro's number. denoted as N with a subscript J at right side. The mass of Avogadro's number of hydrogen atoms will be equal to molar mass of hydrogen. And mass of 6.02 into 10 to power 23 atoms of helium is called the molar mass of helium. Or, we can say, 4.002602 grams of pure sample of helium element will have 6.02 into 10 to power 23 number of helium atoms. So far, we have learned about pressure and temperature and their units, and that the amounts are expressed in terms of moles. Now it's volume's turn. Volume is measured in the units like milliliters, cubic centimeters, cubic decimeters, etc. Molar volume, or volume of 1 mole of a gas, can be calculated by considering the standard conditions of pressure and temperature. In older times, Celsius scale was more popular. Molar volume was calculated equal to 22.414 cubic decimeter, called as the molar volume at standard temperature and pressure, or STP. At STP, temperature is 0 degrees Celsius and pressure is 180 M. In later years, when absolute or Kelvin scale was also used, molar volume of a gas is 24.789 cubic decimeters, called the molar volume at standard ambient temperature and pressure, SATP. At SATP, temperature is 298 Kelvin and pressure is 1 bar or 100 kilopascals. At this point, one should have learned about the 4 state functions of an ideal gas, which are more than enough to describe a gas. Now we can calculate different values and units of general gas constant R. As PV equals nRT, R equals PV over NT. At STP, R equals 180 M into 22.414 cubic decimeter over 1 mole into 273 Kelvin. This is equal to 0.082 cubic decimeters 80 M per Kelvin per mole. In SI units, pressure is given in pascals. 180 M equals 101,325 pascals, which is equal to Newton per meter squared. And volume is expressed in cubic meters. 22.414 cubic decimeters are equal to 0.022414 cubic meters. Then R in SI units will be equal to 101,325 Newton per meter squared into 0.022414 cubic meters over 1 mole into 273 Kelvin, which is equal to 8.3143 Newton meter per Kelvin per mole. Since Newton meter is equal to joules, J, then R equals 8.3143 J per Kelvin per mole. Joule is a unit of energy. 4.18 joules of energy equals 1 calorie. R in calories will be equal to 8.3143 over 4.18 calories per Kelvin per mole, which is equal to 1.987 calories per Kelvin per mole. We now have general gas law and general gas constant for ideal gases. Next thing is the Dalton's law of partial pressure of ideal gases. A gas sample can be pure, or it can be a mixture of gases and other substances. To deal with samples that are a mixture of gases, Dalton's law of partial pressure for perfect gases comes in handy. The law states that the total pressure of a sample is the sum of all the partial pressures of gases present in the sample mixture. P equals PA plus PB plus PC plus and so on. Partial pressures are related to the mole fractions of gas as follows. Pj equals xjp, where x is mole fraction, equal to xj equals nj over n, where n with subscript is the individual moles of a component of the mixture, and n as the denominator is the total number of moles. The sum of all the fractions in the mixture should be equal to 1. Therefore, we can write xa plus xb plus xc plus continues to xj equals 1. Dalton's law of partial pressure and related laws are very useful from academic point of view, as well as in our daily lives. In our daily lives, we mostly encounter with mixture of gases. Everyday analysis of weather is based on studying Earth's atmosphere, which is abundantly available sample for free. Our atmosphere is a mixture of gases, vapor, and particulates from domestic and industrial activities. Atmosphere can be classified in 4 layers of gases, namely stratosphere, troposphere, mesosphere and ionosphere. Weather phenomena takes place in troposphere, which spans up to 11 kilometers above sea level. The regional variations in the physical states like pressure, temperature, and the molar compositions of a mixture of gases in the troposphere decides whether it is going to be sunny, cloudy, rainy, hot or cold day. Generally, within the troposphere, the temperature and pressure decrease as we go away from Earth. The 11 kilometers span above sea level has a long range of varying temperature. Average temperature at sea level is about 15 degrees Celsius. Up to 11 kilometers, the temperature decreases down to -57 degrees Celsius. On thermodynamic scale or Kelvin scale, this would be -57 plus 273 equals 216 K. In this span, the gas molecules, which are moving randomly in the atmosphere, go through different phases. Their distribution in the atmosphere is not very uniform. Some regions have dense air, whereas others have less dense air. These air regions are called parcels. Less dense parcels are warmer, whereas more dense parcels are cooler. The warmer parcel goes further high and becomes cooler. The cooler parcel has high tendency of absorbing water vapor, therefore, it absorbs water vapor present in the atmosphere. The absorption of moisture by cool air results in the formation of clouds. Based on this, one can tell those cloudy skies are associated with the rise of air, and clear skies suggest the descent of air. The cool air may also trap pollutants released from vehicles. This mixture of cool air, vapor, and pollutants is called smog, which is frequently produced in winters of cities like Delhi, Lahore, and Los Angeles. In this lecture, we learned about gas laws for ideal gases. In next lecture, we will talk about the behavior of gases in reality.